Let's talk about the ratio and the root tests. Our last two tests we're going to be learning here with convergence tests with series. So we know quite a few already. These are our last two. So let's start with the ratio test. So if we have some type of series of non-zero terms, this can converge if you take the ratio of the next term of the series over the first term of the series, and that's less than 1. It diverges if you take that same limit. It's greater than 1. If it equals 1, then the ratio test is inconclusive. A lot of examples we've been doing before, what if I spouted out choice number 3? That's why we haven't really talked about the ratio test. So let's talk about some cases here where the ratio test will apply. So if we look here, now what I really try to do is I try to do the nth term test like all the time, real quickly in my head. That limit's going to equal 0, so the nth term test is not going to work. So let's go ahead and use the ratio test because there's nothing really to compare here. So let's do that. So what I'm going to do is, so for a sub n plus 1 for this case, I'm just going to add plus 1. So this is going to be 2 to the n plus 1 all over n plus 1 factorial. Okay? So all I'm doing is just taking n and then doing n plus 1. So if I take the limit, as n approaches infinity, of the absolute value of 2 to the n plus 1 all over n plus 1 factorial divided by 2 to the n all over n factorial. Do just a little bit of rewriting here. Flip the second, multiply. This is going to give me the limit n approaches infinity of 2 to the n plus 1 all over n plus 1 factorial times this right here. And what's nice is I can kind of rewrite this stuff a little bit. So that for that 2 to the n plus 1, and this is what we're always going to be doing for these, that's just going to be rewritten as 2 to the n times 2, because technically that is 2 to the n plus 1. And this n plus 1 factorial, you would always just write this as n plus 1 times, it would be n times n minus 1. So I would really just take out the n plus 1 part, because this is the same thing as n plus 1 factorial. All right, so I got to get comfortable with this kind of stuff. And the reason we do this is because we're going to start to see some cancellations here. So everything here is going to be positive, so I guess those absolute values really are not necessary anymore. So what's going to end up happening here is I'm going to get these 2 to the n's canceling out. Boom, boom. I'm going to get these n factorials to cancel out. Boom, boom. And I'm going to be left with the limit as n approaches infinity of 2 over n plus 1, which is going to equal 0, which is less than 1. So this is going to converge, again, because I'm using the first one right here. This is going to converge by the ratio test. All right. And that's really it. All these problems are like all the same, except they might get a little bit trickier arithmetically, but that's about it. So looking at B here, got all these wacky terms. Let's go ahead and find the limit as n approaches infinity of, and if you don't mind, I'm just going to start off with this right here. I'm just going to take the n plus 1, that instead of writing it like this first, I'm just going to multiply it by the flip version. So I'm going to get n plus 1 squared 3 to the n plus 1 plus 1, so it's n plus 2, all over 2 to the n plus 1 times flipping the original here. And again, these are all going to be positive anyway, so there's no reason to keep the absolute values. So I'm kind of just leave that alone, but I do want to play around with this a little bit here. N plus 1 squared, there's nothing I can do there. But this 3 to the n, I can play around with that one a little bit here. Yeah, so I'm going to get n plus 1 squared 3 to the n times 3 squared all over 2 to the n times 2 times 2 to the n on top, n squared 3 to the n times 3 that's just me rewriting out all this stuff. And let's start finding out what cancels out. That's gone, that's gone, that's gone, that's gone. That square is going to take away that 3. So all I'm left with here is going to be the limit of n approaching infinity of n plus 1 squared times 3 all over 2n squared. And if you expand this out, your coefficient would be n squared, so it'd be 3n squared. So this is actually just going to be 3 over 2 because I have that n squared top and bottom. Coefficients are just 3 over 2. And that is greater than 1. So therefore, I'm going to say that this diverges. Again, you always have to mention the test. All right, that's the ratio test. And then one more example. More or less the same. I guess our conclusion here will be what gets a little wonky here. So we're going to do the limit n approaches infinity of my n plus 1, so n plus 2 factorial all over 3 to the n plus 1 times flip it, 3 to the n all over n plus 1 factorial, absolute value of that. When you do realize everything's going to be positive, because again, we're starting at 1. Okay, so when you realize everything's going to be positive, it's not a big deal. You can drop the absolute value. But we will rewrite this to be n plus 2 times n plus 1 factorial all over 3 to the n times 3 to the n all over n plus 1 factorial. So we're going to get boom, 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 boom. So we're going to get, looks like just n plus 2. So this is going to be the limit n approaches infinity of n plus 2 over 3, which if you plug in infinity, will get infinity, which is indeed greater than 1. So therefore, this is also going to diverge by the ratio test. Okay, that's the ratio test. Go ahead and talk about the root test. Now, the root test is super easy to sniff out because, well, there's a root somewhere. You're going to have if you have a power to the n, it's root test time. So if you take, it's kind of the same idea here. If you take the nth root of the series, it's less than 1, converges. Nth root greater than 1 diverges, equals 1. It's useless to us. So essentially, it's going to be the exact same thing we've been doing. So I would really say that this would be a to the n, absolute value to the 1 over n. It's really our first step that we're going to do, is we're going to do the power to the 1 to the n. Okay? So here we go. So you see how these have powers of n's? Yeah, it's root test time. So let's go ahead and do this as the limit as n approaches infinity of e to the 2n all over n to the n to the 1 over n. Okay, so that's exactly what we're going to do here. This is always going to be positive, so I'm not worried about the absolute values. This is the same thing as the limit as n approaches infinity of e squared over n to the n. Do you agree? Because they both have a power of n. And this is all to the 1 over n. So what's going to end up happening here is he's going to cancel out. So you're going to be left with the limit as n approaches infinity of just e squared over n. And this is getting smaller and smaller and smaller. So this is going to equal 0, which is less than 1. Therefore, this thing is going to converge. So we're going to converge by the root test. That's it. Last one, it's already nicely set up for us. Everything's to the power n. So all we're going to do here is just find the limit. Again, if you plug in a 1, everything's positive. So don't worry about the absolute value. So we're going to get 3n plus 4 all over 2n to the n to the 1 over n, because again, I'm trying to use the root test here. N's are going to cancel out, and you're left with the limit n approaches infinity of 3n plus 4 all over 2n, which is powers are the same top and bottom, so you're going to get 3 over 2. So you get 3 over 2, which is bigger than 1. Therefore, the series is going to diverge by the root test. And then that wraps up all of our tests that we have gone through. That's it.